10 billion worlds in this galaxy sit at the right distance from their stars for liquid water to exist. Each one warmed by real light, shaped by the same chemistry that built you. NASA's Kepler Space Telescope proved it. Rocky planets in habitable zones are everywhere. The distances stretch thousands of light years. The energy to cross them rivals stars. The time required outlasts the civilizations attempting it. For 6 decades, science has asked why the cosmos is silent. The answer emerged from 6 branches of physics, each sealing a different door. Not that life is rare, that the laws which create it also guarantee it stays apart. Tonight we trace those barriers, measure the prison they build, and confront what they mean. If journeys like this speak to you, a like and subscribe go a long way. Settle in. This one reaches far. Start with a number that should fill you with hope. 400 billion. That is a conservative estimate for how many stars burn inside the Milky Way right now. 400 billion nuclear furnaces converting hydrogen into helium, pouring light and heat into the vacuum, warming whatever worlds happen to orbit nearby. Some of those stars are ancient. Red dwarfs that ignited before Earth existed and will still be burning trillions of years after our sun goes dark. Others are young and reckless, blue supergiants, luminous and enormous, destined to exhaust themselves in a few million years and detonate in explosions visible across the galaxy. Most fall somewhere between these extremes. Ordinary stars living ordinary stellar lives for billions of years. And around those ordinary stars orbit ordinary planets, where the ordinary laws of chemistry have had billions of years to do extraordinary things. We know this because we counted them. In 2009, NASA launched a spacecraft called the Kepler Space Telescope into its own orbit around the Sun. Kepler had a single job. It stared at a patch of sky in the constellation Cygnus, one narrow window containing over 150,000 stars, and it watched. For 4 consecutive years, it monitored the brightness of every one of those stars, looking for dips. Tiny, periodic decreases in starlight caused by a planet passing between its star and the telescope. Those dips are extraordinarily subtle. An Earth-sized planet crossing a Sun-sized star blocks roughly 1/100% of that star's light. Detecting that signal requires instruments of extraordinary precision and patience, measured not in months, but in years. Kepler found thousands of planets, not dozens, not hundreds, thousands. Rocky worlds smaller than Earth, gas giants larger than Jupiter, planets orbiting so close to their stars that their surfaces glow with molten rock, planets orbiting so far out that their atmospheres freeze into crystal shells, planets in systems with 2 suns, where the sky holds a double sunrise that science fiction imagined decades before nature confirmed it, planets orbiting dead stellar remnants, white dwarfs and pulsars, the collapsed husks of stars that exhausted their fuel long ago. Planets in configurations no theorist had predicted. The most common type of world Kepler discovered does not even exist in our own solar system. A planet larger than Earth, but smaller than Neptune. A category so unexpected, it did not have a name when the mission launched. William Barucki, the scientist who spent decades championing the mission before NASA approved it, had wagered his career on the idea that planets were common. He proposed the concept in the 1980s. He was rejected. He proposed it again. Rejected again. He refined the instruments, argued for the precision, and kept pushing until the mission finally flew. The data proved him spectacularly right. Before Kepler, we had confirmed a few hundred exoplanets. After Kepler, the count exceeded 2,600 confirmed worlds, with thousands more candidates awaiting verification. The telescope did not just find planets, it rewrote the census of the galaxy. When scientists Extrapolated Kepler's findings across the full stellar population of the Milky Way, the conclusion was staggering. On average, every star in our galaxy hosts at least one planet. Many host several. Some harbor entire planetary systems as architecturally complex as our own. The total planetary population of our galaxy likely exceeds 1 trillion individual worlds. 1 trillion. If you could visit one planet per second without pausing to sleep or breathe, the tour would take more than 31,000 years. The universe builds worlds with astonishing generosity. The question is how many of those worlds can sustain the kind of chemistry that eventually looks up and asks questions. Not all of them can. Most, in fact, cannot. Many orbit too close to their parent stars, baking under radiation fierce enough to strip atmospheres and boil oceans into vapor. Others drift through the frozen outer reaches of their systems, where temperatures plunge hundreds of degrees below zero, and any surface, water, locks into ice, kilometers thick. Gas giants lack solid surfaces entirely. Their atmospheres descend into crushing pressures where no recognizable biology could function. Some worlds orbit wildly elliptical paths, swinging from scorching proximity to their star out into the frigid dark and back again, their surface conditions lurching between extremes that no stable chemistry could survive. Others are rogue planets, ejected from their systems entirely, drifting through interstellar space with no star to warm them at all. The universe scatters planets everywhere, but it is selective about which ones get to play the game. Between the extremes of fire and ice, however, lies a region astronomers call the habitable zone. This is the band of orbital distances where conditions might allow liquid water to persist on a planet's surface. Not too close, where water boils. Not too far, where water freezes. The boundaries are not sharp lines. They are gradients that depend on atmospheric composition, planetary mass, geological activity, and a dozen other variables that shift from world to world. A planet with a thick carbon dioxide atmosphere can trap enough heat to extend the habitable zone further from its star. A planet with a thin atmosphere and no greenhouse effect might freeze even at a distance where Earth would be comfortable. The zone is a starting point, not a verdict. But it tells you where to look. The zone shifts depending on the star. Around a dim red dwarf, it hugs close. So close that a habitable planet may orbit its star in a matter of days, completing a full year in less time than a week on Earth. Around a luminous blue star, the zone stretches far outward. Around a star like our Sun, it falls in a comfortable range that includes Earth's orbit. A reassuring coincidence that reminds you your own existence is consistent with the rules being described here. Liquid water is not a guarantee of life, but it is the only solvent in which every known biochemical process operates. Proteins fold in water. The double helix of genetic material replicates in water. Cell membranes organize in water. Amino acids assemble into functional chains in water. Every organism on Earth, from bacteria thriving in volcanic vents on the ocean floor to lichens clinging to alpine rock faces, depends on liquid water at the molecular level. Where liquid water endures for billions of years, chemistry has the time and the medium to experiment its way toward complexity. So how many worlds have it? Conservative estimates suggest that roughly 20% of Sun-like stars host at least one rocky planet within their habitable zone. The Milky Way contains somewhere between 10 and 20 billion Sun-like stars. That yields between 2 and 4 billion potentially habitable worlds, orbiting stars similar to our own. Think about that for a moment. Billions of worlds with the right temperature for oceans, orbiting just one type of star. But Sun-like stars represent only a small slice of the galactic population. Red dwarfs, which make up approximately 70% of all stars in the galaxy, also host rocky planets in their habitable zones. And this is where the numbers become difficult to hold in your mind. In 2017, a team led by Michael Gillen announced the discovery of 7 rocky planets orbiting a single red dwarf called TRAPPIST-1, just 40 light-years from Earth. 40 light-years. In galactic terms, that is next door. 3 of those 7 worlds sit squarely within the habitable zone. 1 small, dim, unassuming star, and 3 rolls of the dice for life, all within the same system. When red dwarf systems are included in the calculation, the total number of potentially habitable worlds in the Milky Way climbs toward 10 billion, possibly higher, and our galaxy is just one among 2 trillion in the observable universe. 10 billion worlds where liquid water might flow, 10 billion chemical laboratories running experiments in molecular complexity across timescales measured in billions of years. Hold that number, feel the weight of it, because everything that follows depends on what you believe that number means. If the emergence of life is extraordinarily unlikely, requiring some fantastically rare coincidence of mineral catalysts, energy gradients, and molecular luck, then even 10 billion habitable worlds might produce only a handful of living planets. Perhaps life is a fluke, a 1 in a billion accident that happened to occur here and almost nowhere else. Under that assumption, our galaxy might contain fewer than 10 biospheres, each one a lonely island of biology in an ocean of sterile rock and gas. The numbers that seemed so hopeful a moment ago become almost meaningless. 10 billion chances sounds generous until you realize the odds of any single chance paying off might be astronomically small. But there are reasons to suspect life is not that rare. Real, empirical, measurable reasons that come not from optimism, but from the geological record of the one world where we know for certain that chemistry crossed the threshold into something alive. Earth formed 4.5 billion years ago from the debris of earlier stellar generations. For several hundred million years after that, the young planet endured a relentless bombardment, asteroids and comets slamming into its surface with enough energy to melt rock and vaporize oceans. The heaviest of this bombardment tapered off roughly 4 billion years ago. Only then did conditions stabilize enough for liquid water to persist, for temperatures to settle, for the surface to become something other than a furnace. And then, almost immediately, life appeared. The oldest confirmed chemical signatures of biological activity on Earth date to approximately 3.7 billion years ago. Isotopic ratios in ancient rock formations in Greenland carry the fingerprints of carbon chemistry that only living organisms produce. Some researchers argue the evidence pushes even earlier, to 3.8 or 3.9 billion years ago, though the oldest claims remain debated. What is not debated is the speed. Life did not wait. It did not take billions of years of failed chemistry before the right combinations stumbled together. It emerged within a few 100 million years of the surface becoming habitable, possibly sooner. Here is why that speed matters. If the origin of life required a fantastically unlikely accident, some 1 in a trillion convergence of minerals, energy, and molecular luck, you would expect it to take a very long time. Billions of years of nothing, and then a sudden, improbable breakthrough. That is what extreme rarity looks like against a geological clock. Instead, life appeared almost as soon as the planet allowed it, as though the chemistry of carbon and water leads to biology with something approaching inevitability. The dice were thrown, and they came up alive on nearly the first roll. This observation has led some astrobiologists to a striking conclusion. If life arises readily wherever the conditions permit, then it is not rare. It is not a fluke. It is a predictable consequence of chemistry operating on the right ingredients for long enough. And if that is true, the number of living worlds in our galaxy is not 10 or 100. It is billions. Billions of biospheres, each running their own experiments in evolution, scattered across the disk of the Milky Way. But here is where the picture fractures, because life and intelligence are not the same thing. On Earth, single-celled organisms dominated the planet for roughly 2 billion years before anything multicellular appeared. Complex animals took another billion years beyond that. The genus Homo arrived roughly 2 million years ago. And technological civilization, defined as the capacity to build radio transmitters, launch spacecraft, or otherwise make your presence detectable across interstellar distances, has existed for approximately 2 centuries, 200 years out of 4.5 billion. Life may be common. Intelligence that builds technology may be vanishingly rare. There is no way to know from a sample size of 1. Peter Ward and Donald Brownlee made exactly this argument. They proposed that while microbial life might be widespread, the convergence of astrophysical, geological, and biological conditions required for complex life is extraordinarily unlikely. A stable star, a planet with plate tectonics, a large moon to stabilize axial tilt, a magnetic field strong enough to shield the surface from stellar radiation, a gas giant in the outer system to deflect the worst of the asteroid bombardment. Remove any one of these, and the path from microbe to mind may never complete. The universe might be teeming with bacteria and utterly devoid of anyone capable of noticing. This is the tension at the heart of the problem. The optimistic reading of the evidence says life is everywhere and intelligence is a matter of time. The pessimistic reading says life is everywhere and intelligence is a matter of luck so extreme that it may have happened only once. Both readings are consistent with the same data. Both are defended by serious scientists, and neither resolves the fundamental question: how many civilizations are out there right now, in this galaxy, at this moment? In 1961, an astronomer named Frank Drake gathered a small group of scientists at the Green Bank Observatory in West Virginia to ask exactly that question. The meeting was informal, barely a dozen people in a room scribbling on a blackboard. But what Drake wrote on that board became one of the most famous expressions in science. The Drake equation breaks the question of how many civilizations share the galaxy into a chain of smaller questions, each one feeding into the next. How many stars form in the galaxy each year? What fraction of those stars have planets? What fraction of those planets develop life? What fraction of living worlds produce intelligence? What fraction of intelligent species build detectable technology? And, this is the term that haunts every estimate, how long do those technological civilizations survive? Multiply the answers together, and you get an estimate for the number of communicative civilizations active in the galaxy at any given time. The equation is elegant. It organizes ignorance beautifully, and that is precisely its limitation. Most of its terms remain unknown. The rate of star formation is well constrained. The fraction of stars with planets, thanks to Kepler, is now well constrained. But beyond that, each successive term carries uncertainty that spans not just percentages, but orders of magnitude. The fraction of planets that develop life could be 1 in 2 or 1 in a trillion. Nobody knows. The fraction that produce intelligence could be nearly inevitable or effectively zero. Nobody knows that either. The final term, how long a civilization lasts, is perhaps the most important of all, and we have no data whatsoever beyond our own uncertain trajectory. For decades, optimists plugged in generous values and arrived at thousands or tens of thousands of civilizations populating the Milky Way. Pessimists plugged in conservative values and arrived at numbers closer to 1, us alone. The equation generated conversation. it did not generate consensus. Then, in 2018, 3 researchers at Oxford changed the framing. Anders Sandberg, Eric Drexler, and Toby Ord published an analysis that did something deceptively simple. Instead of choosing single best guess values for each unknown term, they asked what happens when you represent each term as a distribution, a range of plausible values reflecting genuine scientific uncertainty. When you multiply distributions instead of point estimates, the mathematics behave very differently. The optimistic mean might suggest millions of civilizations, but the distribution has a long tail stretching towards 0. And when they ran the calculation, they found a substantial probability, roughly 1 chance in 3, that we are the only technological civilization in the entire observable universe. Think about what that means. Not in the galaxy, in the observable universe. 2 trillion galaxies, and possibly no one else. The Fermi paradox asks where everybody is. Sandberg, Drexler, and Ord suggested that the question might be malformed. The silence might not need an exotic explanation. It might simply reflect reality, that the uncertainties in the Drake equation are so vast that our solitude is a plausible outcome of the maths, not a paradox at all. But that is the extreme case. And this video does not rest on extremes. Adopt a more moderate position, and the picture is still striking. Assume life arises on roughly 1 in every million habitable worlds. That gives you 10,000 living planets in the Milky Way. Assume 1 in every 1,000 of those produces a technological civilization. That gives you 10. 10 civilizations active in the galaxy right now. 10 is a small number, vanishingly small compared to 400 billion stars and 1 trillion planets. You could search for 1 billion years and never stumble across one by accident. And yet 10 civilizations in a single galaxy would represent one of the most profound facts in the history of science. It would mean we are not alone. It would mean intelligence is a repeatable outcome of cosmic evolution. It would mean that somewhere right now, another species is building instruments, asking questions, staring at stars that include our sun, without knowing we are here. But 10 civilizations also means something else, something far less hopeful. It means those civilizations are separated by distances so vast that the word distance barely applies. The Milky Way is not a small place. It spans approximately 100,000 light-years from edge to edge. Its disk, where most stars and planets reside, measures roughly 2,000 light-years in thickness. If you treat the galaxy as a flattened cylinder, which is a reasonable approximation of its shape, its total volume encompasses something on the order of 15 trillion cubic light-years. That is the arena. 15 trillion cubic light-years of space, mostly vacuum, sprinkled with stars and planets, separate by gaps measured in light. Now scatter 10 civilizations randomly across that volume. The mathematics of spatial distribution in 3 dimensions is not intuitive, but it is precise. For 10 points distributed uniformly through 15 trillion cubic light-years, the expected separation between closest neighbors works out to roughly 11,600 light-years. Say it slowly. 11,600 light-years. Light itself, moving at 300,000 kilometers per second, the absolute maximum speed permitted by the laws of physics, would need 11,600 years to cross that gap. A radio signal broadcast from one civilization would not reach its nearest neighbor until more than 100 centuries later. A reply would take equally long. The round-trip delay exceeds 23,000 years. When the signal was sent, the last ice age had not yet ended. By the time a reply arrived, human civilization as we know it would be unrecognizable. Every empire that has ever risen and fallen, every language that has ever been spoken and forgotten, every war and every peace, all of recorded human history, would fit inside a nainase single leg of that exchange, with room to spare. Increase the number of civilizations and the distances shrink. But not as dramatically as intuition suggests. Volume scales with the cube of radius, which means you need to multiply the number of civilizations by 8, just to halve the nearest neighbor distance. 80 civilizations yield an average gap of roughly 5,800 light-years. 1,000 civilizations, extremely optimistic figure, bring the average down to approximately 2,500 light-years. 2,500 light-years is still an almost incomprehensible distance. It is roughly the distance from our Sun to the Orion Nebula. Even at velocities far beyond anything human technology has achieved, the journey times stretch across millennia. To ground this in something the human brain can attempt to process, consider an analogy. Shrink the entire Milky Way galaxy down to the size of the continental United States, roughly 3,000 miles from coast to coast. At this scale, our entire solar system becomes a speck smaller than a grain of pollen. The nearest star, Proxima Centauri, sits about 4 inches away. Now place 10 people randomly across the country, between New York and Los Angeles. No roads, no vehicles, no landmarks, just open terrain stretching to the horizon in every direction. The average distance between any two of those people is roughly 900 miles. Each person knows the others exist somewhere out there, but they cannot see them, cannot hear them, and have no way to reach them on foot within a human lifetime. Now, restore the galaxy to its actual size. Replace miles with light years. Replace terrain with hard vacuum irradiated by cosmic rays and devoid of any resources, any fuel, any shelter. The distances between civilizations are not metaphors for loneliness. They are physical realities imposed by the geometry of a galaxy containing 400 billion stars spread across 100,000 light-years of space. Even when you assume intelligent life is common, even when you grant 1,000 civilizations burning simultaneously, the sheer volume of the Milky Way guarantees that each instance of intelligence sits in profound isolation, and the galaxy itself is just one among 2 trillion in the observable universe. Andromeda, the nearest major galaxy, lies 2.5 million light-years away. The Virgo cluster sits 54 million light-years distant. The observable universe stretches 93 billion light-years across. Civilizations arising in separate galaxies face distances so stupendously vast that the gaps within a single galaxy look almost cozy by comparison. But there is something else that makes this picture worse. Something that most discussions of interstellar distance overlook. The galaxy is not uniformly hospitable. You cannot scatter civilizations evenly across its full volume, because most of that volume cannot produce them. In 2004, Charles Lineweaver, Yeshi Fenner, and Brad Gibson published a paper that defined what they called the galactic habitable zone. The idea is deceptively simple. Just as individual planets have habitable zones, orbital bands where conditions permit liquid water, the galaxy itself has a habitable zone, a region where conditions permit complex life to emerge and persist. And that region is far smaller than the full disk. Move too close to the galactic center, and the environment becomes lethal. Stellar density increases dramatically. Stars are packed so tightly that gravitational interactions can destabilize planetary orbits over time. Supernova rates climb steeply. The inner galaxy hosts more massive stars that burn fast and die violently, showering surrounding systems with radiation intense enough to strip atmospheres and sterilize surfaces. A planet orbiting a star near the core might develop life a dozen times, only to have it erased by the death of a neighboring sun. The galactic center is bright, dense, and energetic. It is also, in all likelihood, barren. Move too far toward the outer rim and a different problem emerges. The outer disk is metal poor. Heavy elements, carbon, oxygen, silicon, iron, the building blocks of rocky planets and organic chemistry, are forged in stellar cores and scattered by supernova. In regions where fewer generations of stars have lived and died, the raw materials for terrestrial worlds are simply less available. Stars in the outer disk are more likely to host gas-poor, ice-rich systems. Rocky planets, with the chemical complexity necessary for biology, become increasingly scarce the further out you go. The galactic habitable zone sits between these extremes, an annular band stretching from roughly 4 to 10 kiloparsecs from the galactic center. Our Sun orbits at approximately 8 kiloparsecs, comfortably within the zone, but not at its center. This band represents a fraction of the galaxy's total area. It is the strip where metallicity is high enough for rocky planet formation, but supernova rates are low enough that biospheres can persist for the billions of years that complex evolution requires. The zone is not static. It has expanded outward over cosmic time as successive generations of stars have enriched the disk with heavier elements. Regions that were too metal poor for rocky planets 3 billion years ago may be fertile now. Regions that were within the zone early in the galaxy's history may have since been overrun by the increasing stellar density of the inner disk. The habitable zone is a moving target, and civilizations arising at different times in galactic history would have arisen in different locations within it. The patchwork is not just spatial, it is temporal. Here is why this matters for the distance problem. If civilizations can only arise within this annular band, they are not spread uniformly through the full volume of the galaxy. They are concentrated in a ring that is wide, certainly, spanning thousands of light years in every direction by Gi, but far more constrained than the full disk. In one sense, this brings civilizations slightly closer together, because you are no longer distributing them across the empty outer regions or the hostile inner core. But, in another sense, it changes nothing fundamental. The annular volume is still measured in trillions of cubic light years. Even 1,000 civilizations scattered across that ring remain separated by thousands of light years of vacuum. The geometry is inescapable. Whether you assume 10 civilizations or 1,000, whether you distribute them across the full galaxy or only within the habitable annulus, the result is the same. The nearest neighbor is far, not far in the human sense of a long drive or a difficult flight. Far in the sense that light, the fastest thing permitted by physics, needs thousands of years to make the crossing. And light does not carry passengers. Light does not carry cargo. Light does not carry hope in any physical form. It carries information, and even that information arrives so late that the sender may no longer exist by the time it is received. So the question shifts. The galaxy is vast, and the distances are real. But could something cross them? Could a vessel, a probe, or even a crewed ship bridge the gap between two civilizations separated by thousands of light years of empty space? To answer that, you need to understand what fills the space between stars. And the answer, almost nothing, turns out to be far more dangerous than it sounds. Interstellar space contains, on average, roughly 1 atom per cubic centimeter. To appreciate how empty that is, consider the air in the room where you are sitting right now. Every cubic centimeter of it holds approximately 25 billion molecules. That is not a typo. 25 followed by 18 zeros. The atmosphere you are breathing is a thick, dense soup of nitrogen and oxygen compared to the void between stars. If you could somehow remove all the air from a sealed chamber and pump it down to the best vacuum achievable by the most advanced laboratory equipment on Earth, that vacuum would still contain roughly 10,000 molecules per cubic centimeter. Interstellar space is tens of thousands of times emptier than even that. It is a vacuum so thorough that individual atoms can travel for years without encountering another particle. But empty does not mean safe. Cosmic rays thread through interstellar space at all times. These are not gentle phenomena. They are high-energy particles, protons, helium nuclei, and heavier atomic nuclei, accelerated to staggering velocities by ancient supernovae, colliding neutron stars, and other violent astrophysical engines scattered across the galaxy. On Earth, your atmosphere and the planet's magnetic field absorb the most dangerous ones before they reach the surface. You live at the bottom of an ocean of air that acts as a shield. A vessel in deep interstellar space has no such protection. It sits exposed to a constant rain of particles carrying energies that can shatter molecular bonds and damage living tissue one impact at a time. Alongside the cosmic rays, microscopic dust grains drift through the void. Silicate and carbon particles, each one smaller than a grain of smoke, distributed at vanishingly low densities, roughly 1 grain per 100,000 cubic meters. Sparse beyond imagination, but present across every light year of any journey. At low speeds, these hazards are manageable. A slow-moving vessel encounters cosmic rays and dust impacts at energies that shielding can absorb. The danger is real but containable. At the velocities required for meaningful interstellar travel, velocities we have not yet discussed but will shortly, these same particles become something else entirely, something closer to weapons. And there is nothing else out there. No fuel depots, no rest stops, no raw materials that could be harvested to extend a journey or repair damage. No sources of energy beyond what the vessel carries or can capture from the faint glow of distant stars. The interstellar void is not merely empty. It is aggressively, comprehensively devoid of anything useful to a traveler. A vessel that enters this void carries everything it will ever need for the entire duration of the journey, which may span centuries or millennia, or it does not survive. There is no rescue. There is no resupply. There is only what you brought and the distance still ahead of you. This is the playing field. This is the arena across which any attempt at interstellar contact must unfold. And it is into this arena that the second wall now rises, not from the emptiness of space, but from the deepest structure of space itself. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that quietly demolished any future hope of crossing the galaxy with ease. Albert Einstein was not trying to kill interstellar travel. He was trying to understand the relationship between space, time, and the speed of electromagnetic radiation. But the theory he produced, special relativity, revealed something so fundamental and so unyielding that more than a century of subsequent physics has only reinforced its authority. The speed of light is not merely a measurement, it is a structural property of space-time itself. It is the rate at which causality propagates through the universe, the speed at which cause and effect are connected, and nothing that carries mass, no ship, no probe, no passenger, can ever reach it. The speed of light in vacuum measures approximately 299,792 kilometers per second. To give that number texture, a photon leaving the surface of the sun reaches Earth in roughly 8 minutes. That same photon could circle the entire planet 7.5 times in a single second. Light is so fast that for almost every purpose in daily human experience, it appears instantaneous. Your ancestors can be forgiven for assuming it was infinite. It is not infinite. And the universe is built on scales that expose this finitude with ruthless clarity. Light requires 4 years and 3 months to reach the nearest star system, Alpha Centauri. It needs roughly 26,000 years to reach the center of our galaxy. It takes 100,000 years to cross the Milky Way from edge to edge, the most probable distance between neighboring civilizations, somewhere between 2,500 and 11,600 light years, means that even light needs millennia to bridge the gap. And light, remember, is the fastest thing permitted by the laws of physics. But the speed of light is more than a cosmic speed limit. It is a wall with teeth. The closer any massive object approaches it, the more violently the universe pushes back. This is not a metaphor. It is a measurable, experimentally confirmed consequence of special relativity. And it manifests through three interlocking effects that together make relativistic travel an energy problem of almost incomprehensible proportions. The first is relativistic mass increase. As an object accelerates toward the speed of light, the energy required to accelerate it further does not grow linearly. It grows according to the Lorentz factor, a mathematical function that starts gently and then climbs toward infinity. At 50% of light speed, the Lorentz factor is approximately 1.15. The object resists further acceleration as though its mass has increased by 15%. Manageable, perhaps, for a sufficiently advanced civilization. At 90%, the factor reaches 2.29. The object behaves as though it has more than doubled its rest mass. At 99%, the factor climbs to 7.09. At 99.9%, it reaches 22.4. The curve steepens without limit, approaching infinity as velocity approaches the speed of light. To actually reach it, you would need to supply infinite energy to any object with mass. Not a very large amount of energy, infinite. This is not an engineering limitation awaiting a clever workaround. It is a mathematical boundary as firm as the statement that you cannot divide by zero. The second effect is time dilation. A clock aboard a vessel moving at a significant fraction of light speed ticks more slowly than a clock at rest. At 50%, time aboard the ship passes at roughly 87% of the stationary rate. At 90%, the ratio drops to about 44%. At 99%, time aboard the vessel crawls at barely 14% of the external rate. For the travelers, the journey feels shorter. But for everyone else, for the civilization that launched them, for the civilization they are traveling toward, the full uncompressed duration passes. Time dilation is sometimes presented as a loophole, a way to cheat the distance problem. It is not. It changes who experiences the weight. It does not reduce the weight itself. The third effect is length contraction. From the perspective of a vessel moving at relativistic speeds, distances in the direction of travel appear compressed. At 90% of light speed, a 10 light-year gap appears to shrink to roughly 4.4 light-years from the ship's frame of reference. But the contraction is frame-dependent. Observers at the origin and destination measure the full uncontracted distance. The energy required to make the trip corresponds to the full distance, not the compressed distance perceived aboard the ship. Length contraction changes what the travelers see. It does not change what the journey costs. These three effects are not theoretical speculations. They are among the most thoroughly verified predictions in all of physics. Every particle accelerator on Earth confirms relativistic mass increase every time it operates. The Large Hadron Collider at CERN accelerates protons to 99.999991% of light speed, and the energy required to push them through that final infinitesimal fraction matches Einstein's equations to extraordinary precision. Time dilation has been confirmed using synchronized atomic clocks flown on aircraft and aboard satellites. The Global Positioning System would drift by roughly 10 kilometers per day if its software did not correct for relativistic time differences between orbiting satellites and ground-based receivers. Special relativity is not a hypothesis. It is operational technology. You use it every time you check a map on your phone. Now apply these principles to the problem of interstellar travel. And observe what happens to the energy budget. Consider a spacecraft with a payload mass of 1,000 metric tons. This is roughly the mass of a large naval destroyer, a vessel capable of carrying several hundred crew members, along with life support systems, provisions, and scientific equipment. It is a modest payload by the standards of a civilization attempting to cross interstellar distances, barely sufficient for a skeleton crew on a one-way journey. A more realistic vessel might mass 10 or 100 times more, but start with 1,000 tons and give the physics every possible advantage. The energy costs of accelerating this vessel reveal a staircase of escalating impossibility. Each step upward in velocity does not simply add difficulty, it multiplies it, compounding on the step before in a progression that rapidly overwhelms any conceivable energy source. At 1% of the speed of light, roughly 3,000 kilometers per second, the vessel moves faster than any macroscopic object humans have ever propelled. The New Horizons probe, the fastest spacecraft humanity has launched, reached approximately 16 kilometers per second. 1% of light speed is nearly 200 times faster. The kinetic energy required is approximately 4.5 times 10 to the power of 18 joules. Written out in full, that is 4.5 billion joules. It is roughly equivalent to the energy released by the largest thermonuclear weapon ever detonated, the Soviet Tsar Bomba, multiplied by 20. It approaches 1% of humanity's total annual energy consumption, directed into a single object. Staggering, but theoretically within reach of a civilization that has mastered nuclear fusion. The problem is that 1% of light speed is uselessly slow for the distances involved. At this velocity, the journey to a neighbor 2,500 light years away takes 250,000 years. That is longer than the entire existence of anatomically modern humans. The vessel would arrive at its destination long after the species that built it had either gone extinct or evolved beyond recognition. Step up to 10% of light speed. The journey compresses to 25,000 years. Still enormous, but conceivably within the lifespan of a civilization that endures for 1 million years. The kinetic energy, however, has not merely increased tenfold. It has increased roughly 100-fold, to approximately 4.5 times 10 to the power of 20 joules. This is roughly equivalent to the total energy consumption of human civilization over an entire year. Every power plant, every reactor, every engine on Earth running for 12 months poured into a single spacecraft. And that is the energy budget for acceleration alone. Deceleration upon arrival doubles it. A round trip quadruples it. At 30% of light speed, the journey takes roughly 8,300 years. Relativistic effects are beginning to bite, adding roughly 5% to the effective mass. The kinetic energy climbs to approximately 4.3 times 10 to the power of 21 joules. This exceeds the total energy consumption of human civilization over 7 consecutive years. Every power source on Earth running continuously for 7 years to accelerate one modest spacecraft. Including deceleration doubles it to 14 years of total global output. And this accounts only for the payload. The fuel has not yet entered the calculation. At 50% of light speed, the journey takes 5,000 years. The Lorentz factor has added roughly 15% to the effective payload mass. The kinetic energy reaches approximately 1.4 times 10 to the power of 22 joules. More than 24 consecutive years of total human energy consumption, packed into a single vessel. We have entered a regime where the energy requirement for one ship exceeds what our entire civilization produces in a generation. And we're still talking only about the kinetic energy of the payload itself, the bare minimum, before accounting for the fuel required to deliver that velocity. At 90% of light speed, the Lorentz factor has more than doubled the effective mass. The kinetic energy climbs to approximately 1.6 times 10 to the power of 23 joules. This is roughly 200 years of total human energy consumption. But the kinetic energy is only the beginning. At this velocity, the total mission energy, including fuel, climbs to the equivalent of more than a century of total solar output. Not human energy output, solar output. Everything the sun produces, sustained for over 100 years, funneled into the acceleration and deceleration of a single vessel carrying a payload roughly the weight of a naval destroyer. A Kardashev Type II civilization, one that captures the entire energy output of its host star, would need to save that energy for over a century before it could afford a single round trip at 90% of light speed. And the sun is a modest star. Civilizations orbiting dimmer red dwarfs would face energy deficits even more severe. This escalation is not incidental. It is the defining feature of relativistic physics applied to propulsion. The energy does not scale linearly with velocity. It does not even scale with the square of velocity as it would under classical mechanics. It follows a curve that steepens relentlessly, punishing every additional kilometer per second with disproportionately greater energy demands. The universe has structured its physics so that slow travel is cheap and fast travel is ruinously expensive, with the cost rising toward infinity as the speed of light is approached. Here is what that means, in plain terms. You cannot go fast enough to cross the distances in reasonable time, and you cannot afford the energy to go fast enough to try. The speed limit and the energy scaling are two independent constraints arising from the same underlying physics, and together they form a trap that no amount of engineering can spring. But the energy staircase only describes the cost of moving the payload. It says nothing about how the energy is delivered, and it is here, in the mechanics of propulsion itself, that a second trap closes. Any vessel that carries its own fuel must account for the mass of that fuel, which itself must be accelerated along with the payload. This creates a compounding problem that has haunted rocketry since Konstantin Tsiolkovsky first described it mathematically. To carry enough fuel to reach high velocity, you need more fuel to accelerate the fuel, which requires more fuel to accelerate that fuel. The equation spirals exponentially. It is called the Tsiolkovsky rocket equation, and it is as inescapable as gravity. For a chemical rocket, the kind that has carried every human being who has ever left the ground, reaching even 1% of light speed requires a fuel-to-payload ratio so extreme that the fuel mass exceeds the mass of the observable universe. Chemical rockets are not merely inadequate for interstellar travel. They are ruled out by a margin so vast, it borders on the absurd. The energy density of chemical bonds falls short of the requirement by many orders of magnitude. Nuclear fusion improves the picture considerably. The fusion of deuterium and helium-3 converts approximately 0.4% of the fuel mass into energy, a dramatic improvement over chemical combustion. A fusion-powered spacecraft could theoretically reach velocities of several percent of light speed with fuel-to-payload ratios in the range of 10s to 1. This is the basis for many serious interstellar mission concepts. In the 1970s, the British Interplanetary Society conducted a study called Project Daedalus, a detailed engineering proposal for a fusion-powered probe capable of reaching Barnard's star at roughly 12% of light speed. The vessel massed approximately 54,000 metric tons, fully fueled. The payload was 450 tons. The fuel-to-payload ratio exceeded 100 to 1. And the mission reached only 12% of light speed, a velocity at which the journey to a neighbor 2,500 light-years away would still consume more than 20,000 years. To significantly increase the velocity, the fuel ratio climbs exponentially. At 30%, the ratio reaches thousands to 1. At 50%, the required fuel mass exceeds that of a large asteroid. The exponential scaling is not a technical problem awaiting a better engine. It is a mathematical structure inherent to any propulsion system that carries its own reaction mass. Matter-antimatter annihilation offers the ultimate theoretical energy density. When a particle of matter meets its corresponding antiparticle, both are converted entirely into energy. 100% mass-to-energy conversion. roughly 250 times more efficient than the best fusion reactions. A matter-antimatter drive could theoretically achieve velocities approaching light speed with fuel to payload ratios in the single digits. It is the perfect fuel. It is also, for all practical purposes, impossible to obtain. Antimatter does not exist naturally in usable quantities anywhere in the known universe. Every antiproton used in physics research is manufactured individually in particle accelerators at staggering energy cost. The total antimatter produced by every accelerator on Earth since the technology was invented amounts to roughly 20 nanograms, 20 billionths of a gram. Producing 1 gram, not a kilogram, not a ton, 1 gram, at current efficiencies would require energy inputs rivaling the annual electrical output of entire nations. Producing the kilotons needed for an interstellar voyage would require energy exceeding the total output of the Sun over extended periods. This creates a paradox that cuts to the heart of the energy barrier. The most efficient conceivable fuel requires more energy to manufacture than the fuel itself will provide. You must spend stellar-scale energy to produce the antimatter, then burn the antimatter to propel a vessel that could not reach relativistic speeds without it. The efficiency advantage is real in principle and inaccessible in practice. The universe allows matter-antimatter annihilation. It just makes the antimatter nearly impossible to acquire. Strip away every optimistic assumption, and you are left with a hard physical reality. The speed of light cannot be reached. Approaching it demands energy that scales exponentially. The rocket equation compounds the problem through fuel logistics that spiral beyond planetary masses, and the most efficient theoretical fuel requires more energy to create than it releases. The universe has not built one wall between civilizations. It has built the wall out of layers, each one catching anything that slips through the layer before it. Some propulsion concepts attempt to sidestep the rocket equation entirely by refusing to carry fuel at all. If the energy source stays behind and the vessel rides a beam of externally supplied power, the exponential tyranny of the fuel mass problem vanishes. The vessel accelerates without growing heavier. The physics is clean, and for a brief, exhilarating moment, the maths looks almost favorable. This is the idea behind Breakthrough Starshot. Announced in 2016 by Yuri Milner and Stephen Hawking, the concept envisions an array of ground-based lasers with a combined output of 100 gigawatts, roughly the peak electrical generating capacity of a medium-sized nation, focused onto a reflective sail a few meters wide attached to a spacecraft massing no more than a few grams. The combined photon pressure would accelerate the craft to roughly 20% of the speed of light within minutes. At that velocity, it would reach the Alpha Centauri system in approximately 20 years, a journey that would take conventional propulsion tens of thousands of years, compressed into a single human generation. It is an elegant concept, and for robotic exploration of nearby stars, it may eventually prove transformative, but it does not solve the problem of contact between civilizations. A gram-scale probe cannot carry passengers. It cannot carry life support. It cannot carry the equipment needed to establish any form of physical presence. And crucially, it cannot decelerate upon arrival, because no laser array exists at the destination to slow it down. The probe screams through the target system at 60,000 kilometers per second, collecting data during a flyby that lasts hours at most. It is a camera launched at relativistic speed. It is not a handshake. Scaling the concept to larger payloads introduces catastrophic difficulties. Radiation pressure scales linearly with sail area, but payload mass scales with volume. Increasing the payload from 1 gram to 1,000 metric tons, the minimum for a crewed vessel, requires increasing the laser power by a factor of roughly 1 billion. A 100 gigawatt laser array is an extraordinary engineering challenge that may take decades to build. A 100 exawatt array is a concept so far beyond current capability that the numbers lose physical meaning. The energy required to power such an array during the acceleration phase would exceed the total output of every power plant on Earth combined, sustained for the duration of the burn. Robert Forward first described the physics of laser-pushed light sails in the 1980s, and even he acknowledged that the energy requirements for crewed interstellar missions using this method were vast. The concept works beautifully for tiny probes aimed at nearby stars. It does not work for civilizations trying to physically meet across thousands of light years. At the furthest edge of theoretical speculation sit concepts like the Alcubierre warp drive. In 1994, Miguel Alcubierre published a paper showing that the mathematics of general relativity technically permit a space-time geometry in which a bubble of flat space moves faster than light relative to the external universe. Inside the bubble, the vessel is stationary. The space behind it expands. The space ahead of it contracts. The vessel surfs a wave of space-time distortion, arriving at its destination without ever locally exceeding the speed of light. The mathematics is valid. The physics is almost certainly not. The Alcubierre metric requires exotic matter with negative energy density, a substance that has never been observed in nature and may not be physically possible. Even if exotic matter could be produced, the energy required to sustain a warp bubble capable of carrying a spacecraft has been estimated at the equivalent of the total mass energy of a planet, or in some formulations, an entire star, converted completely into exotic matter. These speculative concepts deserve mention precisely because they illustrate the scale of the barrier. When the most optimistic theoretical physics requires converting Jupiter into a substance that may not exist in order to move a single vessel faster than light, the universe is telling you something about the difficulty of the problem. These are not solutions waiting to be unlocked by better engineering. They are mathematical curiosities that highlight how severely physics constrains travel at and beyond the speed of light. So the propulsion problem offers no escape. Carry your fuel and the rocket equation traps you. Leave your fuel behind and the beam can only push tiny probes. Bend space-time and the energy costs become planetary. Every path through the problem leads to the same conclusion. The distances between civilizations are real. The speed limit is absolute. The energy costs are staggering, and no known or seriously theorized propulsion system can deliver physical contact across thousands of light years at a cost that any civilization could bear. But there is another question buried beneath the engineering, one that does not ask whether a civilization can cross the void, but whether it ever gets the chance to try. In 1998, an economist named Robin Hanson published an essay that reframed the Fermi paradox in terms that cut deeper than distance or energy. He observed that between the raw materials of a lifeless planet and a civilization capable of visibly colonizing the galaxy, a long chain of steps must be completed. Each one must succeed. And the fact that we see no evidence of galaxy-spanning civilizations anywhere in the observable universe tells us that at least one of those steps must be extraordinarily improbable. Hansen called this obstacle the Great Filter. The question it poses is stark. How far along the filter are we? If the filter lies predominantly behind us, in the transition from non-living chemistry to life, or from single cells to complex multicellular organisms, or from animal intelligence to technological civilization, then humanity has already passed through the hardest part. The silence of the cosmos would simply reflect the rarity of what we have already achieved. Our future, in that case, might be open, but if the filter lies ahead of us, in some challenge that technological civilizations routinely fail to survive, then the silence carries a much darker meaning. It means that civilizations reach roughly our level of development, and then, reliably, they stop. They destroy themselves. They collapse under the weight of their own technology. They trigger ecological catastrophes they cannot reverse. Or they transform into something that no longer reaches outward, retreating into virtual environments, rewriting their own biology beyond recognition, or simply losing interest in the stars across timescales measured in millennia. Consider the asymmetry. There are many ways for a civilization to stop attempting interstellar travel. War, environmental collapse, engineered pathogens, resource exhaustion, the unpredictable consequences of artificial intelligence. There are very few reasons to sustain that attempt across the geological timescales required to actually complete it. The window between developing the technology to detect other civilizations and succumbing to the risks that technology creates may be vanishingly narrow. A species might build radio telescopes and nuclear weapons in the same century, and the weapons might win. We have looked for evidence that someone else made it through. For more than 60 years, the search for extraterrestrial intelligence has swept portions of the sky for signals that might indicate a technological civilization broadcasting into space. In 1977, Jerry Ehman detected a 72-second narrowband radio signal at the Big Ear Observatory in Ohio. A burst so unusual, he circled it on the printout and wrote a single word in the margin. The signal has never been detected again. No confirmed artificial signal from beyond our solar system has ever been identified. Freeman Dyson proposed in 1960 that a sufficiently advanced civilization would be detectable not through deliberate broadcasts, but through its waste heat. A civilization that had enclosed its star in a shell of energy-collecting structures, what became known as a Dyson sphere, would radiate in the infrared. Surveys have searched for exactly this signature among nearby stars. They have found nothing that cannot be explained by natural astrophysical processes. The absence of evidence is not proof that no one is there, but it is consistent with a universe in which technological civilizations are either extraordinarily rare, extraordinarily brief, or both. The Great Filter does not tell us which. It tells us only that the filter exists, and that somewhere between lifeless chemistry and a galaxy-spanning presence, something stops almost everything. Whether that something has already stopped us, or is still waiting ahead, remains the most consequential unanswered question in the biology of the cosmos. There is a thought experiment that strips away every comfortable assumption about interstellar contact and replaces them with arithmetic. Imagine you live in a vast apartment building, 10,000 units spread across 500 floors. You know other tenants exist because you can hear muffled sounds through the walls occasionally. A distant vibration, a faint hum. But there is a catch. Each tenant occupies their apartment for only 15 minutes out of every year. They arrive at random times, stay briefly, and leave. You have no schedule, no directory, no way to predict when anyone else will be home. Your 15 minutes might fall at 3 in the morning on a Tuesday in March. Your nearest neighbors might land on a Saturday afternoon in October. You could live in that building for decades and never once overlap with another living soul. Not because the building is empty, not because the tenants do not exist, but because the windows of occupancy are so brief and so randomly distributed that simultaneous presence becomes an event of extraordinary rarity. This is the temporal predicament of civilizations in the Milky Way. The galaxy is not merely vast in space, it is vast in time. And the fraction of that time during which any given civilization exists and possesses the technology to attempt interstellar travel is so vanishingly small that the odds of two such windows overlapping within reachable distance approach the negligible. Start with the age of the galaxy itself. The Milky Way began assembling roughly 13 billion years ago, within the first billion years following the Big Bang. The earliest stars formed from primordial hydrogen and helium. They burned fast, died violently, and seeded the interstellar medium with heavier elements: carbon, oxygen, silicon, iron, the building blocks of rocky planets and organic chemistry. By roughly 10 billion years ago, the galaxy's chemical enrichment had reached levels sufficient for the formation of terrestrial worlds with the molecular complexity necessary for biology. Earth formed 4.5 billion years ago. Life appeared within the first billion years. Complex animals arrived roughly 540 million years ago. The genus Homo appeared 2 million years ago. Anatomically, modern humans have existed for approximately 300,000 years. And technological civilization, the capacity to build machines, transmit electromagnetic signals, or otherwise make your presence detectable across interstellar distances, has existed for approximately 2 centuries. 2 centuries out of 13 billion years. Let that ratio settle. If you compress the entire history of the Milky Way into a single calendar year, with the galaxy forming at midnight on January the 1st, human technological civilization would occupy the final 5/10,000ths of a second before midnight on December the 31st. Not the final second. Not the final millisecond. A fraction of a millisecond so small that it rounds to zero on any scale the human mind can intuitively grasp. This brevity may not be unique to us. Grant the most generous assumption plausible and suppose that a typical technological civilization persists for 1 million years. This is more than 5,000 times longer than humanity has possessed any form of technology. Roughly 3 times longer than the entire existence of the genus Homo. 1 million years represents extraordinary persistence. A civilization that survives every natural disaster, solves every self-inflicted crisis, and maintains interest in physical outreach across timescales that would see continents drift measurably across a planet's surface. Even with this generous assumption, the mathematics of temporal overlap are devastating. A civilization lasting 1 million years occupies approximately 1/13,000th of galactic history. If you selected a random moment from the galaxy's timeline, the probability that it falls within any particular civilization's window of existence is roughly 0.008%. The window is open for an instant, and then it closes permanently, as the civilization either perishes, transforms, or withdraws. Now consider 2 civilizations arising independently at random times during the galaxy's history. 2 intervals of 1 million years placed randomly on a timeline of 13 billion years have an overlap probability of approximately 1 in 6,500, meaning if you repeated the experiment 6,500 times, you would expect the 2 windows to overlap only once. And for that overlap to enable physical contact, the civilizations must not only coexist in time, they must also be close enough in space for a journey to be completed within whatever overlap remains. This is a barrier that operates independently of distance, energy, or the speed of light. Even if you solved every propulsion problem, even if you could teleport instantaneously from one star to another, the temporal mismatch alone would prevent most civilizations from ever sharing the same moment. The galaxy might produce thousands of technological species across its long history, each one burning brightly for 1 million years, and none of them would ever know the others existed. They would occupy the same building. They would never share the same hour. But even 1 million years may be optimistic. The forces that constrain how long any civilization might persist in a state capable of interstellar travel are numerous, varied, and unforgiving. Natural catastrophes operate on timescales that intersect uncomfortably with civilizational lifespans. Asteroid impacts capable of triggering mass extinctions occur roughly once every 100 million years. The Chicxulub impactor, that ended the age of the dinosaurs 66 million years ago, struck with the energy of billions of nuclear weapons, igniting global firestorms, blanketing the atmosphere with debris, and plunging the planet into years of impact winter. A civilization that has not yet developed the technology to deflect such an object, or one that has but fails to detect the threat in time, ceases to exist. The geological record is littered with extinction events. They are not anomalies, they are the schedule. Supernovae within a few dozen light years, close enough to irradiate a planet's surface and destroy its ozone layer, occur at intervals estimated in the hundreds of millions of years. Gamma-ray bursts, the most energetic explosions in the universe, could sterilize a planet's biosphere from thousands of light years away, though their frequency and directionality make precise risk estimates difficult. None of these events are frequent on human timescales, but on galactic timescales they are routine. A civilization that persists for 10 million years is virtually guaranteed to face at least one existential natural threat. Self-inflicted risks may be even more pressing. Industrial civilizations alter their environments at rates that can outpace adaptive responses: climate destabilization, resource depletion, ecosystem collapse, nuclear arsenals, engineered pathogens, and the unpredictable consequences of artificial intelligence all represent threats that operate on timescales of centuries, not millions of years. If any of these pressures commonly leads to civilizational collapse before interstellar capability is achieved, the average lifespan of a technological civilization could be far shorter than the generous million-year estimate. And even without catastrophe, civilizations might not remain interested in physical exploration indefinitely. A species that develops sufficiently advanced computation might retreat into virtual environments, effectively abandoning the physical universe in favor of simulated realities that consume far less energy. A civilization that masters genetic engineering might transform itself into forms unrecognizable as technological agents, something closer to a distributed biological network than a tool-using species. These possibilities are speculative, but they highlight an important asymmetry. There are many paths by which a civilization stops reaching outward. There are very few paths by which it sustains that reach across geological time. Now, stack every condition required for physical contact between two civilizations and observe what happens to the probability. They must be close enough in space, within a few thousand light years at most. They must overlap in time, both existing simultaneously within their brief technological windows. The sending civilization must detect the receiving civilization, which requires that both are active and producing detectable signatures at the same moment. The sending civilization must develop and launch an interstellar vessel, a process that could itself require centuries of technological development. The vessel must survive the journey, enduring millennia of cosmic radiation, dust impacts, and mechanical degradation. And the receiving civilization must still exist when the vessel arrives. Each of these conditions carries its own probability of failure. Each is independent of the others. Multiply them together, and the compound probability of a successful physical meeting drops with each additional requirement, not gradually, but precipitously, like a chain in which every link must hold, and any single failure breaks the whole. The universe does not forbid contact. It permits it in the way it permits a specific, shuffled deck of cards. Technically possible, astronomically unlikely, and functionally indistinguishable from impossible when measured against the timescales involved. The temporal problem extends beyond civilizational lifespans. The stars themselves impose deadlines that no civilization can negotiate. Stars are not permanent. They are engines that burn through finite fuel supplies at rates determined by their mass. And the relationship between a star's mass and its lifespan is not linear. It is steeply inverse. Double the mass and the star does not burn twice as fast. It burns roughly 8 to 10 times faster, because higher mass means higher core temperatures, which accelerate nuclear fusion at rates that far outpace the extra fuel supply. This means the galaxy's stellar population offers radically different habitable windows, depending on which star a civilization happens to orbit. The Sun is a G-type main sequence star with a mass of roughly 1 solar mass and a total hydrogen burning lifespan of approximately 10 billion years. It is currently 4.5 billion years into that lifespan, leaving roughly 5.5 billion years before it exhausts its core hydrogen, expands into a red giant, and eventually sheds its outer layers to become a white dwarf. But long before that final stage, the Sun's increasing luminosity will render Earth uninhabitable. Within roughly 1 billion years, perhaps 1.5 billion at the outside, solar output will have increased enough to trigger a runaway greenhouse effect. The oceans will boil, the surface will sterilize. The habitable window for our planet is not 5 billion years. It is closer to 1 billion. And a significant portion of that window has already been spent. Consider an F-type star, roughly 1.3 times the mass of the Sun. These stars burn hotter and bluer, pouring out more energy per second. Their total main sequence lifespan drops to approximately 4 to 5 billion years. The habitable zone around such a star shifts outward more quickly as the star brightens, leaving planets less time to develop complex ecosystems. If intelligence requires the roughly 4 billion years of prior biological evolution that it took on Earth, F-type stars are marginal hosts. Their habitable windows close before the biological clock finishes ticking, move up to A-type stars, roughly twice the solar mass, and the picture becomes hopeless for biology as we understand it. These stars exhaust their hydrogen in under 2 billion years. Their habitable zones shift so rapidly that stable planetary climates may never form. A-type stars are brilliant, numerous, and biologically irrelevant. They burn too fast for life to get a foothold. At the other extreme sit the red dwarfs. A red dwarf of 0.1 solar masses burns so frugally that its lifespan stretches to roughly 10 trillion years, nearly 1,000 times the current age of the universe. On paper, this seems ideal, an almost unlimited window for life to emerge and evolve. But red dwarfs present severe obstacles. Their habitable zones lie so close that planets become tidally locked, permanently showing one face to their sun. One hemisphere bakes under perpetual daylight, the other freezes in permanent night. Whether a stable climate can develop under such conditions remains an open question. Red dwarfs also produce frequent and violent flares, sudden eruptions of radiation that can exceed the star's normal luminosity by factors of hundreds for minutes to hours. A planet in the habitable zone of an active red dwarf endures periodic radiation storms that can strip its atmosphere over geological time. A planet that loses its atmosphere loses its water. A planet without liquid water loses its chance at life. K-type stars, sometimes called orange dwarfs, occupy an intriguing middle ground. With masses between roughly 0.6 and 0.9 solar masses, they burn steadily for 15 to 30 billion years. More than enough time for intelligence to evolve many times over. They are less prone to violent flaring than red dwarfs. Their habitable zones sit at distances where tidal locking is less certain. Some astrobiologists consider K-type stars the most promising hosts for long-lived biospheres, offering the stability of a red dwarf without the hazards. But even K-type stars are not infinite. Their habitable windows begin and end at specific times in galactic history, depending on when each star formed. This diversity of stellar lifespans creates a patchwork of habitable windows scattered across the galaxy in both space and time. Some star systems reached habitable conditions 8 or 9 billion years ago and have already passed through their window. Whatever civilizations arose around those stars lived and died before our sun even ignited. Their worlds may still orbit, but as barren husks, long since sterilized by their aging stars. Others became habitable more recently, within the last few billion years, and remain within their window. Still others, particularly around younger stars or in regions of the galaxy where metallicity is still increasing, have not yet reached conditions suitable for complex life and will not do so for billions of years to come. Two civilizations need not only exist simultaneously, they must arise around stars whose habitable windows overlap. A civilization that emerged 7 billion years ago around a star that has since left the main sequence cannot be visited today. Its star may be a white dwarf. Its planets either consumed during the red giant phase or stripped to barren cores. A civilization that will not emerge for another 3 billion years around a young star currently in its early main sequence cannot be visited either. It does not yet exist. The travelers would arrive to find a world still billions of years from producing intelligent life. And here lies a dimension of temporal isolation that deserves to be felt, not merely understood. Imagine a civilization that detects a promising signal from a star system 4,000 light-years away. They invest centuries of effort into building an interstellar vessel. They launch it at 5% of the speed of light, the maximum their energy budget allows. The journey takes 80,000 years. During those 80,000 years, the crew, whether biological beings in some form of suspended animation or digital minds running in slow cycles, crosses a void of unimaginable emptiness. They endure cosmic ray bombardment, micrometeorite erosion, the slow degradation of systems pushed far beyond their designed operational lifetimes. And they arrive. They reach the star system that broadcasts the signal. They enter orbit around the planet that showed spectral signatures of an oxygen-rich atmosphere and artificial electromagnetic emissions. What they find is silence. The planet's atmosphere has changed. The oxygen signature is gone, replaced by carbon dioxide and methane. The surface shows no artificial structures, no city lights on the night side, no electromagnetic transmissions of any kind. The oceans are still there, but they have turned a deep reddish brown, choked with anaerobic microorganisms that have reclaimed a world left empty. The civilization that sent the signal is gone. Perhaps it destroyed itself. Perhaps it evolved into something unrecognizable. Perhaps a natural catastrophe wiped the slate clean 50,000 years before the vessel arrived. The travelers crossed 80,000 years of void to find a graveyard. Or consider a variant that is somehow more haunting. The travelers arrive and find the planet thriving, covered in life, oceans blue, continents green. But the life is not intelligent. It is complex, multicellular, diverse, but it has not produced minds capable of recognizing visitors. The civilization the travelers sought existed 85,000 years ago. It lasted 300,000 years. It produced art and science and radio signals and dreams of the stars, and then it ended. The biology of its home world continued without it, filling the ecological niches the departed civilization left behind. The planet is alive. The civilization is extinct. The travelers have arrived 60,000 years too late to meet anyone, but early enough to walk on the same ground their hoped-for hosts once inhabited, now populated by creatures that will never know what walked there before them. These scenarios are not dramatic embellishments. They are straightforward consequences of the arithmetic. When journey times are measured in tens of thousands of years and civilizational lifespans are measured in hundreds of thousands to millions, the probability of arriving during the narrow window of a destination, civilization's technological existence is small, and the probability that you will know in advance whether that window is still open is essentially zero. The signal you detected left the source 4,000 years ago. It tells you about conditions 4,000 years in the past. The civilization could have vanished 3,900 years ago, and you would not know for another century. Stars also move. The Milky Way is not a static grid. Stars orbit the galactic center at varying speeds, depending on their distance from the core. The Sun orbits at roughly 220 kilometers per second, completing one full revolution every 230 million years. Over 50,000 years of travel time, the destination star moves approximately 37 light-years due to its own orbital motion. Over 500,000 years, the displacement grows to nearly 370 light-years. The target does not merely drift, it relocates to an entirely different region of the galaxy. A vessel launched toward a star's current position arrives to find empty space. Unless its trajectory accounts for motion that grows increasingly difficult to predict across such spans. The destination is not a fixed point on a map. It is a moving target following a path that grows more uncertain with every additional century of projection. Every barrier discussed so far, the crushing distances, the relativistic speed ceiling, the exponential energy costs, the merciless brevity of civilizational lifespans, the stellar deadlines that close habitable windows before travelers can arrive, operates within a universe that is at least standing still. The void between two stars may be immense, but at least is a fixed immensity. A civilization contemplating a journey of 5,000 light-years can plan around a destination that stays where it is. The gap is daunting, but stable. Except, it is not. The universe is not standing still. It is expanding, and it is expanding faster every year. In 1929, Edwin Hubble published observations confirming that distant galaxies are receding from us, and that the farther away a galaxy sits, the faster it retreats. This was not the motion of objects flying apart through a static space like shrapnel from an explosion. It was something stranger and more fundamental. Space itself is stretching. The fabric of the cosmos is physically expanding, carrying galaxies along like specks embedded in a surface that is being pulled apart from every direction simultaneously. The galaxies are not racing away from us through the universe. The universe between us and the galaxies is growing. Hubble's law quantifies this expansion through an elegant linear relationship. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by approximately 70 kilometers per second. At modest distances, this effect is negligible. The Andromeda Galaxy, 2.5 million light-years away, is actually falling toward us under mutual gravitational attraction. Its inward velocity more than overcomes the expansion of the intervening space. Within the gravitationally bound neighborhood of galaxies known as the local group, expansion does not dominate. Gravity holds things together. But beyond the local group, expansion rules. At distances of hundreds of millions of light-years and beyond, galaxies recede at thousands of kilometers per second. And the most distant objects we can observe are racing away at velocities that approach and exceed the speed of light. That last sentence deserves a pause. Objects receding faster than light. This appears to violate Einstein's cosmic speed limit. It does not. Special relativity prohibits objects from moving through space faster than light, but it places no restriction on how fast space itself can expand. The galaxies beyond a certain distance are not moving through space at superluminal velocities. They are stationary within their local region of space, but the space between them and us is accumulating so rapidly that the total separation increases faster than light could ever cross it. The distinction is subtle but physically precise, and its consequences are absolute. At a distance of approximately 14 billion light-years, the recession velocity equals the speed of light. This boundary is called the Hubble radius, and it marks a critical threshold. Beyond it, space expands faster than photons can traverse it. A light signal emitted from a galaxy beyond the Hubble radius, aimed directly at Earth, will never arrive. Not because the signal is too faint, not because something blocks it, but because the space the photon must cross is growing faster than the photon can cover it. the signal falls behind, like a swimmer stroking against a current stronger than any stroke can overcome. It moves forward through local space at the full speed of light, and yet it falls farther behind with every passing second, because the total distance it still needs to cross keeps increasing faster than it can close the gap. This is not a technological limitation. There is no hypothetical amplifier, no relay station, no ingenious engineering scheme that can circumvent this barrier. It is a geometric property of expanding space-time. The photon is traveling at the maximum speed permitted by physics. The space is expanding at a rate determined by the energy content of the universe. When the latter exceeds the former, no causal connection is possible. No signal, no ship, no force of any kind can bridge the gap. The two regions become what physicists call causally disconnected. They exist in the same universe, governed by the same laws, but they can never interact, never communicate, never influence each other in any way, for the remainder of cosmic time. For civilizations, this means something very specific. Any intelligence that arises in a galaxy beyond the Hubble radius is not merely far away. It is gone, permanently, structurally, and irrevocably severed from any possibility of contact with us, or with any civilization in our corner of the cosmos. It could be ancient, brilliant, desperate to communicate, broadcasting at maximum power in every direction. None of it would matter. The expanding universe has placed a wall between us that thickens with every passing second and will never be breached. For decades, cosmologists assumed that the expansion was at least slowing down. Gravity, the mutual attraction between all matter, should act as a cosmic brake, gradually decelerating the expansion, even if it could never fully halt it. The universe was flying apart, but it was flying apart less quickly with each passing era. Or so everyone expected. In 1998, two independent research teams shattered that expectation. The Supernova Cosmology Project, led by Saul Perlmutter out of Berkeley, and the High-Z Supernova Search Team, led by Brian Schmidt, with Adam Rees conducting the critical data analysis, were both studying distant Type 1a supernova, a particular class of stellar explosion whose intrinsic brightness is well understood, making them extraordinarily useful as cosmic distance markers. If you know how bright something truly is, and you measure how bright it appears, the difference tells you how far away it is. Both teams measured the distances to dozens of these explosions scattered across billions of light years of space. Both teams expected to find that distant supernova were brighter than predicted, which would mean the expansion was decelerating, as gravity demanded. Both teams found the opposite. The distant supernova were dimmer than expected, farther away than they should have been. The expansion was not slowing down, it was speeding up. The discovery came as a shock, even to the scientists who made it. The result was so unexpected that both teams spent months searching for errors before publishing. They found none, and the fact that two rival groups, working independently with different telescopes and different analysis methods, had reached the same conclusion made the finding almost impossible to dismiss. The expansion is not decelerating, it is accelerating. Space is stretching faster with every passing era, driven by a pervasive, poorly understood component of the cosmos called dark energy. Dark energy constitutes approximately 68% of the total energy content of the universe. It permeates all of space with a constant energy density that does not dilute as the cosmos expands. This is what makes it so extraordinary and so dangerous. Normal matter and radiation become less dense as space grows. Their fixed quantity spreads across increasing volume. Dark energy does not thin out. Its density remains constant per unit volume, which means that as new space is created by expansion, new dark energy fills it automatically. The more space exists, the more dark energy exists. and the stronger the repulsive effect becomes. Expansion creates space. Space contains dark energy. Dark energy accelerates expansion. Expansion creates more space. The cycle feeds itself without limit. This accelerating expansion has a consequence that may be the most profound and least appreciated fact in all of cosmology. The cosmic event horizon is shrinking. Not the observable universe, which continues to grow as ancient light reaches us for the first time, but the event horizon, the boundary beyond which events occurring right now will never be observable to us. Because expansion is accelerating, galaxies that are currently within our observable volume are being carried across this horizon at an increasing rate. Once a galaxy crosses the event horizon, no event occurring there, no signal emitted, no light produced, will ever reach us. The galaxy does not vanish in a flash. Its light redshifts gradually, stretching to longer and longer wavelengths, dimming asymptotically toward invisibility. But the outcome is the same. The galaxy is gone, not destroyed, not hidden, simply removed from the realm of possible interaction, permanently and irreversibly. Currently, roughly 97% of the galaxies within our observable volume are already receding faster than light. We can see them only because their light began its journey billions of years ago, when they were much closer, before expansion carried them beyond the critical threshold. Every photograph of the deep universe is a portrait of objects we can observe but never touch. We are looking at their past. Their present is already unreachable. Their future belongs to a realm we will never enter. The observable universe, the sphere of space from which light has had time to reach Earth since the cosmos became transparent 13.8 billion years ago, currently measures approximately 93 billion light-years in diameter. This number exceeds the age of the universe multiplied by the speed of light, because space has been expanding throughout the entire journey time of every photon we receive. Objects that emitted light toward us billions of years ago were much closer then. The light has been traveling ever since, but expansion has carried those objects to distances far exceeding what light travel time alone would suggest. The cosmic microwave background, the oldest light we can detect, was emitted from matter that was roughly 42 million light-years away at the time of emission. That same matter now lies 46.5 billion light-years away, carried outward by 13.8 billion years of cosmic expansion. Within this vast observable sphere sit approximately 2 trillion galaxies, but this collection represents only what we can see. Measurements of the spatial curvature of the cosmos indicate that space is flat to extraordinary precision, which implies that the universe extends far past our observational horizon. The total universe may measure at least 250 times the diameter of the observable sphere. The region we can access, the fraction of reality from which light has had time to reach us, may constitute less than 1% of what actually exists, and the situation is worsening. With every passing moment, more of the observable universe slips beyond the event horizon. The accelerating expansion is not a distant future concern. It is happening now, quietly, continuously, irrevocably, redshifting galaxies one by one into permanent silence. Within the gravitationally bound local group, roughly 80 galaxies, including the Milky Way and Andromeda, expansion does not dominate. Gravity holds these galaxies together. The space between them is not stretching fast enough to overcome their mutual attraction. The Milky Way and Andromeda are approaching each other at roughly 110 kilometers per second. In 4 to 5 billion years, they will merge, their stars threading past one another in a slow, gravitational dance that will eventually produce a single, massive, elliptical galaxy. The local group is an island of gravitational coherence in an ocean of accelerating expansion. But beyond that island, every structure is receding. And the timeline of loss is not abstract. It follows a specific, calculable schedule that astronomers can project with confidence based on current measurements of the Hubble constant and the dark energy density. The Virgo cluster, 54 million light-years away, the nearest major concentration of galaxies, will cross the cosmic event horizon within approximately 100 billion years. That is a long time by any human measure, but it is finite, and it is a deadline. Every civilization in the Virgo cluster that we have not contacted by then becomes unreachable for eternity. Not for a long time, for eternity. The Coma cluster, roughly 320 million light-years distant, crosses the horizon sooner. Its higher recession velocity carries it beyond causal reach within approximately 80 billion years. The great walls and filaments of the cosmic web, the largest structures in the observable universe, stretching across hundreds of millions of light-years, will fragment and dissolve from our causal volume over similar timescales. Each structure that crosses the event horizon is not merely lost to observation, it is lost to interaction. It can never again affect or be affected by anything in our local group. Think about what that means for civilizations in those clusters. A technological species arising in the Virgo cluster right now, looking outward, detecting galaxies in every direction, building a picture of the cosmos that includes the Milky Way in it, has a window measured in tens of billions of years, during which intergalactic contact with us is at least theoretically possible. However impractical the distances and energies involved might make it. When that window closes, it closes permanently. No future technology, no future breakthrough, no amount of patience or ingenuity will reopen it. The expansion will have carried them beyond the speed of light, and the gap will only grow wider from that moment forward. Within approximately 150 billion years, every galaxy outside the local group will have crossed beyond the cosmic event horizon. Every single one. The Virgo cluster, the Coma cluster, the Great Attractor, the Shapley supercluster, all of them redshifted beyond detection and passed permanently out of causal contact. Future observers inhabiting the merged remnant of the Milky Way and Andromeda will look outward and see nothing. Not darkness. Darkness implies the absence of something that should be there. They will see a cosmos that appears to contain a single galaxy surrounded by perfect, infinite emptiness. The cosmic microwave background will have redshifted to wavelengths so long that no conceivable instrument could detect it. There will be no observational evidence that other galaxies ever existed, no evidence that the Big Bang occurred, no evidence that the universe was ever anything other than a single galaxy floating in a static, eternal void. The entire history of cosmic expansion, the most dramatic story physics has ever told, will have erased all traces of itself. This is not a distant hypothetical disconnected from the question of civilizational contact. It is directly relevant because it establishes an absolute upper boundary on which civilizations can ever interact. Any two civilizations residing in separate gravitationally bound structures, in different galaxy groups or clusters, face a hard deadline imposed by cosmic expansion. If they do not establish contact before expansion carries them beyond mutual causal reach, they never will. The deadline is not negotiable. It is not contingent on technological advancement. It is a consequence of the geometry of space-time under accelerating expansion, and no technology operating within the laws of physics can circumvent it. For civilizations in separate galaxies, this deadline may already have passed. A civilization in a galaxy currently receding from us faster than the speed of light is already beyond reach. No vessel launched today, at any speed up to and including the speed of light, will ever arrive there. They could be broadcasting at maximum power in every direction. We would never receive a single photon. Within the Milky Way itself, cosmic expansion is not the dominant factor. Gravitational binding holds the galaxy together. The barriers within our galaxy remain the speed limit, the energy abyss, the temporal mismatch, and the stellar deadlines. But expansion eliminates the possibility of assistance or rescue from beyond. If the answer to the Fermi paradox lies in some other galaxy, if a civilization somewhere in the Virgo cluster has solved the problems of interstellar travel within their own galaxy, they cannot help us. They cannot reach us. The expanding universe ensures that intergalactic travel is not merely difficult. For the vast majority of galaxy-to-galaxy combinations, it is physically impossible, and the window during which it was even theoretically possible is closing. Now assemble the full architecture of isolation, every barrier layered upon every other. Not quickly, slowly, because the weight of this argument depends on understanding that these are not different descriptions of the same problem. They are 6 independent problems arising from 6 different branches of physics, each one sufficient on its own to make interstellar contact extraordinarily difficult, together forming a compounded barrier whose total strength exceeds the sum of its parts. The first wall is spatial separation. Civilizations, even if common, are separated by thousands to tens of thousands of light years within a single galaxy. This is a consequence of stellar density and galactic volume, of how matter distributes itself across a disk 100,000 light years wide containing 400 billion stars. It is a fact about geometry. It cannot be reduced by any technology. You can build faster ships. You cannot make the galaxy smaller. The second wall is the speed of light, an absolute ceiling on the velocity of any massive object, not a speed suggestion, not a guideline, not a technological barrier that cleverer engineering might sidestep. A structural property of space-time, confirmed to more decimal places than any other physical law in history. It arises from the deepest structure of special relativity, a framework so embedded in modern physics that overturning it would require dismantling electromagnetism, particle physics, and cosmology simultaneously. No serious physicist expects this to happen. The third wall is the exponential energy scaling compounded by the rocket equation. As velocity increases toward the speed of light, the energy required does not grow proportionally. It climbs along a curve that steepens relentlessly toward infinity, and the rocket equation compounds this by demanding that fuel mass grows exponentially with the desired velocity, creating a spiraling trap in which reaching meaningful fractions of light speed requires fuel masses exceeding moons, asteroids, and eventually planets. This barrier arises from thermodynamics and the mathematics of momentum conservation. It applies to every propulsion system that obeys the laws of physics, which is all of them. The fourth wall is temporal isolation. Technological civilizations exist for brief intervals relative to galactic time. Even granting million-year lifespans, an extraordinary act of generosity. The probability that 2 civilizations coexist within overlapping temporal windows and within travel range of each other is small. The journey times required to cross the separating distances frequently exceed the lifespans of the civilizations attempting them. This barrier arises from biology, ecology, and the statistics of existential risk. It is independent of physics entirely. It would constrain contact even if faster travel were possible. The fifth wall is stellar deadlines. Stars have finite habitable windows determined by their mass and evolutionary stage. Civilizations arising around different stellar types experience habitable windows that may not overlap. A civilization that thrived 7 billion years ago left no destination for a civilization arising today. A civilization that will emerge 3 billion years from now offers no target for one that exists right now. This barrier arises from stellar astrophysics and the nuclear physics of hydrogen fusion. It operates on timescales of billions of years and determines which stars can support life and for how long. The sixth wall is the accelerating expansion of the universe. Beyond the gravitationally bound local group, every galaxy is receding. Most of the observable universe is already causally disconnected from us. Intergalactic travel is physically impossible for the overwhelming majority of galaxy pairings, and the window for what remains is closing. This barrier arises from general relativity and observational cosmology. It is the most absolute of the six, because it imposes not merely difficulty, but impossibility across the largest scales. Each of these walls operates independently. Each arises from a different branch of physics. They are not different facets of a single obstacle. They are six separate walls nested inside each other, each one catching anything that slips through the wall before it. A civilization that solves the energy problem still faces the speed limit. A civilization that achieves high velocity still faces the temporal mismatch. A civilization that happens to coexist with a neighbor still faces the distance. A civilization that exists in another galaxy faces expansion. The barriers do not compete with each other. They collaborate. Each one covers the gaps left by the others, forming a prison with no single point of failure. Multiply the probabilities. Even using the most generous assumptions at every stage, abundant life, common intelligence, million-year lifespans, overlapping habitable windows, achievable propulsion. The compound probability of two independently arising civilizations physically meeting each other drops to a figure so small that it functionally rounds to zero. Not exactly zero. Physics does not forbid a civilization from launching a vessel at 1% of light speed toward a destination star and arriving 100,000 years later to find another civilization in its technological prime, ready and willing to make contact. It is permitted, but the probability that all necessary conditions are satisfied simultaneously, spatial proximity, temporal overlap, sufficient energy, survivable journey, persistent destination, is so low that across the entire history of a galaxy the size of ours, it may never happen once. This is the resolution the universe offers to the apparent paradox of cosmic silence. The question is not where is everybody? The question is malformed. It assumes that the existence of other civilizations implies the accessibility of other civilizations. Physics makes no such guarantee. The universe may be saturated with intelligent life, thousands of civilizations burning across the Milky Way's history, millions scattered across the 2 trillion galaxies of the observable universe. And yet, the architecture of the cosmos, the distances, the speed limits, the energy barriers, the temporal mismatches, the stellar deadlines, and the relentless expansion ensures that virtually none of them will ever physically encounter another. The silence is not evidence of absence, it is evidence of structure. The universe is built to produce life in isolation, not by malice, not by design, simply by the operation of the same physical laws that allow stars to burn, planets to form, and chemistry to become biology. The laws that create life also create the prison. The same relativity that governs the nuclear reactions powering stars also limits the speed at which anything can travel between them. The same gravity that pulls gas clouds into stellar nurseries also determines that galaxies spread across millions of light years of void. The same dark energy that accelerates cosmic expansion also ensures that most of the universe is permanently beyond reach. Creation and isolation emerge from the same equations. They are not in tension. They are the same phenomenon viewed from different angles. Some have proposed that self-replicating probes could circumvent the distance and lifespan problems. The idea, first explored through the theoretical framework of von Neumann machines, imagines a civilization launching a single probe toward a nearby star. Upon arrival, the probe uses local resources to build copies of itself, which then launch toward further stars. Each copy builds more copies. The wave of probes expands exponentially, reaching every star in the galaxy within a few tens of millions of years. A tiny fraction of galactic time. If any civilization had ever done this, the argument goes, we should see evidence of their probes everywhere. The absence of such evidence is sometimes cited as proof that no civilization has ever reached the required technological level. But this argument assumes that probes can survive indefinitely, replicate flawlessly across millions of generations, and continue functioning across timescales that would see their parent civilization transform or vanish many times over. It assumes that the energy and material requirements for self-replication in alien star systems are manageable. It assumes that the probes would remain detectable after millions of years of operation and entropy. Each assumption carries uncertainty, and the temporal barrier remains. Even a galaxy seeded with self-replicating probes 10 billion years ago would offer nothing to a civilization arising today if the probes ceased functioning or evolved beyond recognition in the intervening aeons. The galaxy could be littered with the dormant remains of 1,000 probe networks, each one launched by a civilization that no longer exists, and we would have no way to distinguish them from natural debris. The silence, then, is not a mystery requiring exotic explanation. It is the predictable outcome of a cosmos that creates life with breathtaking generosity, and then places each instance of life in a box of distance, energy, and time so large that escape seems almost inconceivable. Almost, not certainly. And it is in that slender gap between almost and certainly that the meaning of our situation reveals itself. There is a temptation to receive this as tragedy, to feel the weight of cosmic loneliness pressing down. The knowledge that however many civilizations have gazed at alien skies and wondered, they are almost certainly doing so alone. The vessels never launched, the signals never received, the handshake across the void never completed. Two intelligences, each burning with curiosity, separated by a gulf that neither can cross. But there is another way to hold this knowledge. Consider what the universe has accomplished. From an initial state of unimaginable density and temperature, it expanded, cooled, and organized itself into structures of staggering complexity. It built atoms from subatomic particles. It forged those atoms into stars. It cooked heavy elements in stellar cores and scattered them across light years in supernovae. It gathered those elements into planets. It stirred them with energy, and it waited. In at least one case, and probably in billions of cases, the waiting paid off. Chemistry became biology. Biology became complexity. Complexity became awareness. You are that awareness. Atoms that can wonder about atoms. Stardust that can study the stars it came from. The universe spent 13.8 billion years building the conditions for this moment. The moment in which a configuration of matter looks outward and grasps, however imperfectly, the true scale of what exists. That understanding is not diminished by isolation. It is sharpened by it, precisely because you cannot meet the other minds that may exist across the cosmos. Your understanding of the cosmos itself becomes more precious. Every equation derived, every observation recorded, every theory tested represents a civilization reaching as far as its confinement allows. The walls are real. The reaching is also real. And there is something worth noticing about a species that reaches even when it knows the walls are there. The structure of the universe is not a flaw. It is an architecture. The same expansion that isolates civilizations from each other also cooled the primordial plasma into atoms, allowing chemistry to begin. The same distances that prevent contact also prevent a single catastrophe from sterilizing an entire galaxy. The same stellar lifetimes that create temporal mismatches also provide the billions of years of stable energy output that life requires to evolve. Isolation is not the cost of a poorly built universe. It is a feature of a universe built precisely right for the emergence of complexity and awareness, distributed across scales that ensure no single event can extinguish all of it simultaneously. Look up tonight. Every point of light in the sky is a sun. Many of those suns warm worlds. Some of those worlds may harbor oceans, atmospheres, ecosystems. The photons arriving at your eyes have traveled years, decades, centuries, carrying information about places you will never visit. The light connects you to them. The space separates you from them. Both the light and the space are governed by the same physics, emerging from the same fundamental constants, expressed through the same mathematical structures that have operated without interruption since the first fraction of the first second after the cosmos began. Somewhere, separated from you by thousands of light years of vacuum, another mind may be reaching the same conclusion tonight, sitting beneath an alien sky, surrounded by unfamiliar constellations, understanding for the first time that the universe creates life and then keeps it apart, not out of cruelty, not out of indifference, out of geometry, out of physics, out of the deep mathematical structure that makes stars and planets and minds possible in the first place. You will never meet them. They will never meet you. But you share something no distance can erase. You share the same universe. The same laws built you both. The same stellar furnaces forged the calcium in their bones and the iron in your blood. The same cosmic expansion that separates you from each other also gave both of you the time and the space to exist. Every civilization is a window. Every window looks out on the same cosmos. And the cosmos is extraordinary enough to be worth the view, even if the only eyes that ever see it through your particular window are your own. The universe was not built for meetings. It was built for wonder, and in that, it has not failed.